Welcome back to TalkTensors, everyone, for another exciting deep dive into the world of machine learning research.
Indeed.
And today we're going to be looking at a paper that really caught our eye.
Yeah.
It tackles a problem that's been kind of a thorn in the side of reinforcement learning for language models for a while now. You know how we're always striving to make these models learn more efficiently, right?
For sure.
Well, this paper offers a fresh perspective and a potential solution, and it all revolves around this idea of off-policy learning.
Interesting.
The paper is titled Soft Policy Optimization, Online Off-Policy RL for Sequence Models.
Okay, so right off the bat, the title gives us a clue that we're moving away from the traditional on-policy methods like PPO that have been so popular.
Exactly, and that shift to off-policy learning is a pretty big deal. It opens up a whole new world of possibilities for how we can train these models.
I'm curious to hear more about why on-policy methods have limitations, especially for something as complex as language.
Well, think about it this way. With on-policy methods like PPO, the model is constantly learning and updating its behavior based on the data it's generating right now.
Right.
So it's like it has this very short-term memory. It makes a change, gets some feedback, and then kind of forgets the specifics of what just happened.
I see.
The paper argues that this makes these methods really inefficient when it comes to using data. Like, they can't effectively learn from previous training runs, or from all the different ways the model might have explored solutions in the past, or even from examples of what expert humans have done.
That makes sense. It's like trying to learn to write code by only looking at the one program you just wrote, whether it worked or not.
Precisely. You'd be missing out on a wealth of knowledge about different approaches, common pitfalls, best practices, you name it.
And wouldn't that also make exploration really difficult? Especially in something like code generation, where there might be many different ways to solve a problem, and it can take a lot of trial and error to find even one that works.
Absolutely. With on-policy methods, it's like you're stumbling around in the dark, and even if you find a good solution, you don't really get to build on that knowledge effectively because you're so focused on the immediate next step.
So it sounds like these on-policy methods might also struggle with generating diverse outputs.
That's another key point the paper brings up. On-policy RL can sometimes push the model towards just repeating the most likely outputs it was already producing. It's like getting stuck in a rut.
Yeah, that makes sense. Especially for language tasks. We want models that can be creative, that can explore different ways of expressing things, and that can come up with a variety of valid solutions.
Exactly. And from a practical standpoint, training these massive language models often involves distributing the work across many different machines.
Right, because of the sheer size and computational demands.
Exactly. With asynchronous PPO, you end up having to constantly move the model back and forth between the machines that are generating the data and the machines that are actually doing the learning.
Oh, I see. That sounds like it could create a lot of overhead and really slow down the training process.
It does. And to make matters worse, you often need a whole separate neural network just to estimate the value of different actions, which adds even more complexity and uses up more memory.
So there are all these challenges with the traditional on-policy approach. What does this paper propose as an alternative?
This is where soft policy optimization, or SPO, comes in.
SPO.
It's a soft approach to reinforcement learning that aims to address all of these limitations.
Okay, I'm intrigued. How does it work?
At its core, SPO is designed to learn from a much wider range of data, not just the data it's currently generating, but also any relevant data you might already have, like from previous training runs, human-generated examples, or even data from different models.
So it's not just stuck in the present moment.
Yeah.
It can actually leverage past experiences and knowledge.
Precisely. And here's the kicker. It does all of this without needing that separate value estimating network that PPO relies on.
Wow, that's impressive. It sounds like a much simpler and potentially more efficient approach.
It is. And the results they present in the paper are pretty exciting.
Oh, tell me more.
They tested SPO on a challenging code generation task, and it consistently outperformed PPO on a key metric called pass at 10, which measures the probability of getting at least one correct solution within 10 independent attempts.
So it's not just about finding a solution, it's about finding a variety of potentially valid solutions.
Exactly. And that's especially crucial for tasks like code generation, where there might be many different ways to achieve the same outcome.
That makes a lot of sense. So SPO seems to excel at exploring the solution space and coming up with diverse answers.
It does. And on top of that, they saw significant improvements in terms of speed and memory usage. Plus, it was much more stable during training.
This is starting to sound like a real game changer for how we train these large language models.
It very well could be. So let's delve into the paper itself and see how they actually make all this magic happen.
Sounds good. Let's dive in.
The paper is titled, as we mentioned, Soft Policy Optimization, Online Off-Policy RL for Sequence Models. And its core contribution, really, is introducing this SPO algorithm as a new and effective way to apply reinforcement learning to these sequence models, like language models, with the specific goal of overcoming those limitations of on-policy methods that we've been discussing.
Okay, so the main focus is on enabling this off-policy learning capability.
Exactly. And they achieve this through a really clever idea they call cumulative Q-parameterization.
Cumulative Q-parameterization. That sounds interesting. What is that?
It's a way of estimating the value of taking different actions. But instead of using a separate value function like PPO does, it cleverly combines the policy itself with a reference model.
The reference model. Is that like the pre-trained model you start with?
Typically, yes. So you've got your initial pre-trained model, which serves as a sort of baseline, and then you've got the policy you're trying to learn through reinforcement learning.
Okay.
And SPO essentially figures out the value of different actions by comparing how the learned policy would behave compared to this reference model.
That's clever. It's like learning by looking at how your decisions differ from what a more experienced model would do.
That's a great analogy. And crucially, this approach allows SPO to learn from data that wasn't generated by its own current policy, which is what makes it off policy.
Starting to see how this all fits together.
Now let's talk about some of the theoretical underpinnings of SPO. It's based on this framework called KL regularized reward maximization, which is central to soft RL.
KL regularized reward maximization. That's a bit of a mouthful. What does it mean?
Essentially, it means you're not just trying to maximize the reward you get from the environment, but you're also trying to keep your learned behavior somewhat similar to a reference behavior.
Interesting. Why would you want to do that?
Well, there are a couple of reasons. First, it encourages exploration. By not straying too far from the reference behavior, the model is more likely to explore different possibilities rather than getting fixated on a single, potentially suboptimal solution.
That makes sense.
And second, it helps with stability. By making sure the learned policy doesn't change too drastically from the reference policy, you can avoid those sudden jumps in behavior that can sometimes lead to instability during training.
Okay, so it's like a gentle nudge towards better performance rather than a forceful shove that can knock the model off balance.
Exactly. And the way this similarity to the reference behavior is measured is using something called the Kullback-Leibler divergence.
KL divergence, right? I've heard of that. It's a way of measuring how different two probability distributions are.
Precisely. And the best policy in this soft RL setting is one that takes into account this reference policy and adjusts its behavior based on the potential rewards it can get.
So it's like the reference policy provides a starting point and then the RL algorithm fine-tunes it to make it better.
Exactly. Now, to actually implement this soft RL framework, the authors introduced this concept of a token-level soft Q value.
Token-level soft Q value. What's that?
Imagine you're generating a sequence of words or code tokens, one by one. At each point in that sequence, this Q value represents the expected soft reward you would get from that point onwards.
So it's like looking ahead and estimating how well you're likely to do based on what you've generated so far.
Precisely. But it's not just the expected reward under the learned policy. It also takes into account that reference policy for all the future tokens you haven't generated yet.
I see. So it's like factoring in the guidance of that more experienced model.
Exactly. And from this Q value, they define an advantage function for each token, which is simply the difference in Q values between the sequence with that token and the sequence without it.
So the advantage tells you how much that specific token contributed to your chances of success, considering the reference policy.
Exactly. Now, here's where things get really interesting. In traditional RL, you often have to go to great lengths to make sure your value estimates are consistent over time and across different possible paths.
Right. I've heard about these concepts of path consistency and Bellman consistency. They can be a real headache to deal with.
They can be. But the beauty of SPO is that its cumulative Q-parameterization naturally satisfies these consistencies for all the intermediate steps in generating a sequence.
So for all the tokens before the very last one, where you actually see the final reward.
Exactly. And this is a really big deal. It significantly simplifies the learning process.
I can see why that would be a major advantage.
So how does this cumulative Q-parameterization actually work?
I'm all ears.
Well, The Q value at each token is calculated as a running total of the differences in log probabilities, those advantages we just talked about, between the learned policy and the reference policy.
Okay. So you're tracking how much the learned policy is deviating from the reference policy at each step.
Right. And this sum starts from an initial estimate of the value of the prompt itself, which they call Q hat 0.
Q at 0. Got it. So you have to have some initial guess for how good the starting point is before you even start generating anything?
You do. And they estimate this initial value by having the reference policy generate a bunch of possible completions for the prompt before any training even begins.
Interesting. So it's like getting a sense of the average outcome you'd expect from the reference model.
Exactly. And because the Q value is built up step by step based on how the learned policy's choices differ from the reference policy, it automatically stays consistent with the path the model is taking and how the expected future reward is changing along that path.
So path consistency and Bellman consistency are just baked into the way the Q value is calculated. That's really elegant.
It is. And they even prove a really important theoretical result.
Oh, what's that?
They show that this learned Q function will be optimal, meaning it perfectly reflects the true value of different actions, if and only if the policy itself is optimal, and that initial prompt value, Q hat 0, was correct.
So there's this tight link between the quality of the policy, the accuracy of that initial value estimate, and the optimality of the learned Q function.
Precisely. Now, the beauty of all of this is that SPO doesn't need to explicitly enforce Bellman consistency or path consistency through complex loss functions for those intermediate steps. It just happens naturally because of the way the Q value is calculated.
That's amazing. It really simplifies the learning process compared to methods that have to worry about consistency at every single step.
It does. And this means that the main focus of learning becomes making sure that the Q value we get at the very end of the generated sequence, the final token, lines up with the actual reward we observed for that entire sequence.
So the learning process is all about reducing the error between that final predicted Q value and the actual reward.
That's right. And the paper explores several different ways to achieve this.
Like what?
One approach is what they call terminal Q regression, where they simply try to minimize the difference between that final Q value and the observed reward using various loss functions.
What kind of loss functions did they use?
They experimented with things like squared loss and cross-entropy loss, both with and without some additional tricks like clipping or warping to make the learning process more stable.
Okay, so they're trying different ways to measure and minimize that prediction error for the final Q value.
Exactly. And then they also explored something called non-terminal Q regression.
Non-terminal. So that means looking at the Q values for those intermediate tokens, not just the final one.
Right. In this approach, they try to make the Q value at each intermediate token consistent with the final reward, but they subtract out the advantages of all the tokens that come after it.
Subtract out the advantages. Why do they do that?
The idea is to try and assign credit or blame for the final outcome back to the earlier decisions made in the sequence.
That's interesting. It's like trying to figure out which early choices were most responsible for the ultimate success or failure.
Exactly. They call these adjusted targets reverse Q targets.
Reverse Q targets. Got it.
And then there's advantage regression, where they focus on the total sum of advantages over the entire sequence.
Okay.
They try to match this sum to the difference between the final reward and that initial prompt value, Q hat 0.
So again, the goal is to make sure the Q values are accurately predicting the final outcome, but this time they're looking at the overall impact of the policy's decisions throughout the sequence.
Precisely. Now, on top of all of this, the authors also investigated using Monte Carlo methods to get even better estimates for those non-terminal Q values.
Monte Carlo methods. So that involves generating multiple samples and averaging the results, right?
Right, and they focus on what they call pivotal tokens.
Pivotal tokens, what are those?
These are key points in the sequence where the probability of success seems to change significantly.
So like a turning point where the model either makes a good decision that puts it on the path to success or a bad decision that makes success less likely.
Exactly. And they use a technique called pivotal token search to identify these critical moments.
Interesting.
And then they generate multiple sample completions from the reference policy, starting from these pivotal tokens to get a better sense of what the Q value should be at those points.
So they're using the reference model to explore different possibilities and get a more robust estimate of the value at these crucial decision points.
That's right. And these improved estimates then serve as stronger learning signals during training.
It sounds like they're really pulling out all the stops to get the most accurate value estimates possible.
They are. And this attention to detail really pays off in their experimental results.
Now, before we dive into those results, it might be helpful to compare and contrast SPO with PPO, just to highlight how different they really are.
That's a great idea.
Yeah.
So as we've discussed, PPO heavily relies on that separate value function to estimate future rewards, which adds complexity to the model and increases the memory it needs.
Right.
SPO, on the other hand, cleverly weaves the policy and the reference model together to get its value estimates, so it doesn't need that extra value network.
Much more efficient.
And in those distributed training setups where you've got multiple machines working together, PPO faces challenges because it needs to constantly synchronize both the policy and the value models across all those machines.
I could see how that would slow things down.
It does. SPO, because it can learn from data generated by older versions of the policy, doesn't need to be synchronized as frequently, so it can train much faster.
Makes sense.
Yeah.
And what about their ability to handle off-policy data?
Well, PPO can technically use data that's slightly different from what the current policy is generating, using a technique called importance weighting. But it generally performs best with data it has just collected itself.
So it's not truly off-policy in the same way that SPO is.
It's not. SPO, on the other hand, is designed from the ground up to learn from all sorts of different data sources, including data generated by completely different policies or even human experts.
So it's a much more flexible and versatile learner.
It is. All right, now let's finally get to those experimental results.
I'm eager to hear how SPO actually performs in practice.
Well, the authors focused their experiments on a benchmark called code contests, which, as the name suggests, involves generating code to solve various programming challenges.
Sounds challenging.
It is. And they used a pretty powerful language model as their starting point, the Llama 3.18b instruct model.
So a large instruction-tuned language model, that's a good foundation to build on.
It is. And their main evaluation metric, as we mentioned earlier, was pass at 10, which measures the probability of getting at least one correct solution within 10 independent generations.
Right, so it rewards diversity and the ability to explore different solution pathways.
Exactly. And drum roll, please.
Huh? Go on.
SPO, especially when trained with a mix of online data from its current policy and offline data from various sources, significantly outperformed PPO on that pass at 10 metric.
Wow, that's impressive. It really seems to deliver on its promise of generating more diverse and creative solutions.
It does, and they saw this improvement consistently across different variations of the code generation task.
That's compelling evidence.
It is. Now, interestingly, they did observe that PPO tended to do a bit better on the pass at 1 metric, which only checks if the very first generated solution is correct.
So PPO might be slightly better at finding that single most likely answer, but it might be sacrificing exploration and diversity in the process.
That's the interpretation the authors put forward. And it fits with the idea that on-policy methods like PPO might be more prone to converging to a single, highly probable solution, even if there are other equally good or even better solutions out there.
It's like getting tunnel vision and missing the bigger picture.
Exactly. Now let's talk about that offline data that SPO was able to leverage so effectively.
Well, because that's one of its key strengths.
It is. They used a variety of different sources, including samples from that initial reference model, outputs from previous SPO and PPO training runs, and even solutions written by human programmers.
It's a really rich and diverse data set.
It was. And this ability to learn from past experiences, from different approaches, and from human expertise is a major advantage of SPO's off-policy nature.
It makes sense that being able to tap into all of that knowledge would lead to better performance.
It does. And on top of the improved pass at 10 scores, they also reported a substantial speed up in training time, around 85% faster than PPO.
85%? That's a huge improvement.
It is. And this speed up is largely due to the fact that SPO doesn't need to synchronize the model as frequently in those distributed training setups, because it can learn from data generated by older versions of the policy.
Right, so the workers generating the data can keep chugging along without having to wait for the very latest model updates?
Exactly. Now, they also did some ablation studies to figure out which parts of SPO were contributing most to his performance.
Ablation studies. So they removed or modified different components to see how it affected the results.
Right. And they found that using a straightforward squared loss function for that final Q value regression worked quite well.
Keep it simple?
Apparently so.
Yeah.
The impact of trying to regress those intermediate Q values, that non-terminal Q regression we talked about, was a bit more mixed.
Interesting.
But they did see a noticeable improvement when they used those Monte Carlo estimates for the Q values at those pivotal tokens.
So focusing the learning signal on those key decision points seems to really help.
It does. Now, stepping back a bit, it's interesting to think about how SPO's success in maintaining policy diversity relates to the behavior of traditional policy gradient methods like PPO.
Right, because that was one of the key motivations for this work.
It was. The author suggests that PPO and methods like it tend to quickly gravitate towards responses that are already quite likely under that initial reference policy.
So it's like reinforcing existing biases, in a way.
In a sense, yes. But SPO, because it can learn from a much broader range of data, including less probable but still correct solutions that might be found in the offline data, is able to maintain and even increase the diversity of its outputs.
It's like it's able to break free from those initial constraints and explore a wider range of possibilities.
Exactly. Now, to really appreciate the significance of this work, it's helpful to look back at the history of reinforcement learning for language models.
Okay, let's take a historical perspective.
RL really became a hot topic in this area with the success of techniques like RLHF reinforcement, learning from human feedback.
Right, RLHF has been making waves in aligning language models with human preferences.
It has. And on-policy methods like PPO became the go-to approach for implementing RLHF and for fine-tuning language models in general.
But as we've seen, those on-policy methods have their limitations.
They do. And the challenges of needing a lot of data, effectively exploring the solution space, and being able to leverage existing data sets have been persistent problems in the field of RL more broadly.
It seems like those challenges are even more pronounced when you're dealing with the complexity and nuances of language.
They are. And that's where this theoretical framework of soft RL comes in.
Soft RL, right? We talked about that earlier.
It's been around for some time. And it aims to strike a balance between maximizing rewards and encouraging exploration and diversity through that KL regularization term we discussed.
So this paper is really bringing those ideas to the forefront in the context of training large language models.
It is. And it's doing so with a practical and effective algorithm that's showing real promise.
It's also interesting to think about how this relates to human learning. We don't just learn from our own direct experiences. We learn by observing others, by reading about past successes or failures, by drawing on the collective knowledge of our society.
That's a great point. And in a way, on-policy RL has been like each AI agent having to figure everything out on its own from scratch.
Stuck in its own little world.
That's exactly.
Yeah.
But SPO offers a potential path towards a more collaborative, experience-leveraging form of learning for AI.
It's like giving these models access to a vast library of knowledge and letting them build on the experiences of others.
That's a great analogy. So to summarize some of the key takeaways without repeating ourselves too much.
Go for it.
SPO offers a really compelling way to address that data efficiency bottleneck that's been plaguing RL for sequence models.
Agreed.
And it does so through this innovative and theoretically sound cumulative Q-parameterization, which elegantly handles those consistency requirements that have tripped up other methods.
And let's not forget its ability to effectively utilize all sorts of offline data, especially diverse data sets, which can significantly boost both performance and training speed.
Absolutely. And this leads to more diverse and robust policies, which is particularly valuable for tasks like code generation, where there are many different ways to solve a problem.
And from a practical perspective, the reduced need for frequent model updates makes SPO much more scalable when you're training these massive models across many machines.
All really important points. Now, thinking about the bigger picture, what are some of the potential real-world implications of this work?
Well, for starters, we might see much more efficient and effective ways to train these large language models for truly complex tasks. Things that go beyond just following simple instructions like advanced reasoning, intricate problem solving, and generating genuinely creative content.
Those are some exciting possibilities.
They are. And what about the potential for continuous learning? If these models can constantly learn and adapt based on a growing pool of interaction data, including successes and failures from various scenarios and even different models, we could see AI systems that improve at an unprecedented rate.
That's a fascinating idea. It's like a collective intelligence constantly evolving and refining itself.
Exactly. And the ability to learn from a wider range of data could also have a big impact on reducing biases and making these systems more robust.
Right, because if they're exposed to a broader spectrum of perspectives and solutions during training, they're less likely to latch on to spurious correlations or flawed patterns in a limited data set.
Precisely. And we can't overlook the practical benefits of SPO's memory efficiency. Not needing that separate value model means lower computational costs for both training and deploying these models in real-world applications.
Very true. And that enhanced diversity in the generated outputs could be a game changer for applications that require creativity or the ability to explore multiple solution pathways.
Imagine a coding assistant that can suggest several different ways to solve a problem, each with its own advantages and trade-offs, or a writing tool that can help you explore different creative styles.
Those are some compelling examples. All right, now for a bit of fun speculation, it's time for our Novel Notions segment, where we brainstorm some interesting research directions inspired by this paper.
Let's get those creative juices flowing.
All right, so one idea that immediately jumps out at me is the possibility of dynamically updating that reference policy, Pi0, during the SPO training process.
Oh, that's interesting. The paper itself mentions that keeping it fixed is a limitation.
Right. But what if we could continuously refine that reference policy based on what the learning policy is discovering? Imagine it gradually evolving to become more expert over time, incorporating successful strategies and solutions found by the learning policy.
So it's like a student surpassing the teacher and then the teacher learning from the student.
Exactly. It could create a sort of positive feedback loop, potentially leading to even faster learning and better final performance.
I like it.
Yeah.
But you'd probably have to be careful about stability, right?
Definitely. You wouldn't want the reference policy to change too drastically or become too specialized too quickly.
Maybe some form of regularization to prevent those wild swings would be necessary.
Right. And it would be really interesting to see how this dynamic reference policy would affect both the accuracy of the most likely solution, that pass at 1 metric, and the ability to generate a variety of correct solutions, pass at 10.
Yeah, it could lead to some unexpected trade-offs or synergies.
Definitely worth exploring. Now, here's another thought. What about applying SPO to multitask learning or continual learning scenarios for sequence models?
That's an intriguing idea.
Given its strength in learning from diverse offline data, could SPO be more effective at retaining knowledge from previous tasks and adapting to new ones compared to on-policy methods that might tend to overfit to the current task?
It's an interesting question. On-policy methods can be a bit amnesiac, quickly forgetting what they've learned when faced with a new challenge.
They can. But SPO, with its ability to leverage past experiences, might be better suited for these more dynamic learning scenarios.
I agree. Imagine training a language model on a series of different coding challenges, or even different types of language tasks, and allowing it to leverage offline data from all the tasks it's encountered before.
That's the idea. The way SPO builds up its Q value incrementally, incorporating the advantages of different actions, seems like it could lend itself well to transferring knowledge across tasks.
The lessons learned from earlier tasks could provide a valuable starting point for tackling new challenges.
Exactly. And it aligns with the way humans learn. We constantly build on our past experiences and knowledge.
Of course, there would be challenges. You'd need clever ways to manage and weigh the offline data from different tasks, making sure that information from an unrelated task doesn't interfere with learning a new one.
Right. Some sort of task-aware data management would be crucial.
But the potential for creating more versatile and adaptable AI agents through this kind of continual learning with SPO is really exciting.
It is. Imagine coding AIs that get progressively better at each new programming language they learn, or writing AIs that can seamlessly blend different styles they've mastered over time.
Those are some tantalizing possibilities. Of course, these are all just speculative ideas, things to ponder and explore further.
They are. But that's what makes this research so exciting. It opens up new avenues for thinking about how we can train and interact with these powerful language models.
It definitely pushes the boundaries of what's possible.
So to bring this deep dive to a close, let's recap the key takeaways.
It sounds good.
Soft policy optimization, as presented in this paper, introduces a really promising off-policy approach to reinforcement learning for sequence models.
A real departure from the traditional on-policy methods.
It is, and it addresses those key limitations we talked about: data efficiency, exploration, and leveraging existing knowledge by being able to learn from a much broader range of data, including those diverse offline sources.
And it does so with a really clever and theoretically sound approach, that cumulative Q-parameterization, which simplifies the learning process by inherently handling those pesky consistency requirements.
For me, that was a real aha moment. It's such an elegant solution.
It is, and the results they demonstrate in code generation are really compelling, showing improvements in both the ability to generate a variety of correct solutions, pass at 10, and in the speed and efficiency of training.
Absolutely. Now, if you're itching to delve into the nitty-gritty technical details yourself, we've included a link to the paper in the description below.
Definitely worth a read for anyone interested in the future of RL for language models.
And to leave you with a final thought-provoking question: How might the ability to learn from a vast history of AI interactions and solutions, as potentially enabled by methods like SPO, fundamentally change the way we train and evolve intelligent systems in the future?
Will we see a shift towards a more cumulative, experience-driven paradigm for AI development?
That's a question worth pondering. Thanks for joining us on TalkTensors.